Welcome to question 11 from the 2020 TMUA paper 1. The question tells us that a quadratic function passes through the points 2, 0 and Q0, where Q is strictly greater than 2, and that it is shown in this diagram below. The areas R and S are marked on the diagram, and we are asked to find the value of Q such that the area of the region R is equal to the area of the region S. We are given 6 different options for the value of Q. Pause the video and have a go at doing this for yourself. Let's start by reminding ourselves that we're told the function goes through 2, 0 and Q0, which tells us that 2 and Q are roots. And therefore, using this information, can we find an equation for the function? Well, we can apply the factor theorem and use the fact that we can see this parabola is V-shaped to see that the function must therefore have factors x minus 2 and x minus q, and the coefficient of x squared must be positive. So we'll just call it a, where a is some real number which is strictly greater than 0. So this is the equation of the curve, and we now want to find the value of q such that the area R and the area S are equal. So let's just redraw our diagram here after we've expanded out the brackets. And how can we find the area of region R? Well, we can integrate the curve from 0 to 2, and that will give us the area under the curve, which is the area R. So therefore R is the integral from 0 to 2 of our function in the expanded form, and we can integrate this because everything here is just polynomials, so we just add 1 to the power and divide through by it, and we see that we have, therefore, the integral is, factoring out the a third x cubed minus a half q plus 2x squared plus 2qx, and we want to use the boundary points 2 and 0. So if we evaluate this at 0, clearly everything is just equal to 0, and if we evaluate it at 2, we actually find that this is equal to 2q minus 4 thirds. So therefore the area of region R is a times by 2q minus 4 thirds. So now we want to find the value of q such the area of region R equals the area of region S. So we want the area of region S to also equal this value. So the next thing we're going to do is find the area of region S in terms of q. So let's move on to a new page and do that. Okay, so we have our equation for the function, and we've evaluated the area of region R, and we have our sketch here. So now how can we evaluate the area of region S? Well, to find R, we integrated the function from 0 to 2, because that gives us the area under the curve. So how can we find the area of region S? Well, if we integrate the curve from 2 to q, then that will give us the minus 1 times by this area between the curve and the x-axis, and the reason we have that minus factor is because it's below the x-axis. But areas are defined as always being positive, so therefore the area of region S is actually minus 1 times by the integral of the function from 2 to q. So this is the area of region S, and we now need to integrate this function in order to find it. So again, everything's a polynomial here, so we can integrate it, which gives us this form. And now if we plug in x equals q and subtract away x equals 2, because those are our 2 boundary points, we are left with these 2 expressions. And if you expand out all of the brackets and collect the terms, we can see that this is equal to minus a times by minus the 6th q cubed plus q squared minus 2q plus 4 thirds. So if we bring that factor of minus 1 inside the brackets, then we get a 6th q cubed minus q squared plus 2q minus 4 thirds. So this is the area of region S in terms of q. And now if we remember, the question asks us to find the case R equals S. So we have the area of region R, the area of region S, and we can see that these will be equal exactly when these 2 expressions are equal to each other. So we want to find the value of q, which we're told is strictly greater than 2, which satisfies this equation. So our task now is to solve this equation. So how can we do that? Well, we can see we have 2q minus 4 thirds on both sides of this equation, so let's get rid of that from both sides of the equation, and that just leaves us with a 6th q cubed minus q squared equals 0. So what can we do now? Well, we can divide through by q squared, and we can do this comfortably knowing that q isn't equal to 0, because we know that q is strictly greater than 2. So that just leaves us with a 6th q minus 1 equals 0. And if we bring the 1 onto the other side, multiply through by 6, we see this tells us that q must equal 6. So there we go, that's the solution, and if you look back to the start of the question, this was option A. So our answer is A.